Greetings and welcome back to a new video about square wave inverter. In this example we will discuss the square wave inverter having a series RLC load as shown here. We will see that step by step in our calculation and also verify this in MATLAB Simulink simulations. So in the previous examples we have seen that the load was resistive in the first case and then there was resistive and inductive in series, and now we have extended that in this resistive, inductive and capacitive, so RLC. The values of the components are shown here, and we have again a VDC here, DC voltage source of 100 volts, and the switching frequencies again 60 Hz as before. Again, we would like to calculate some parameters that are all shown here. Let's look at our solutions. The load voltage and the load current can be determined together using the following analysis. The load voltage is expressed using the Fourier series as shown here. We have here the summation of the odd indexes, and we have an amplitude here and also the sine formula with the index n, which then increases the frequency. The formula for the amplitude is shown here, which is the 4 times VDC over n pi, where n is 1, 3, 5, etc. So only odd. And the omega 0 is our fundamental frequency or the switching frequency, which is 2 pi times 60 Hz. Now the load current is related to the load voltage using actually Ohm's law and of course the impedance. So that is actually shown here. So, and there is a phase shift. So we see here again amplitudes, again n times the fundamental frequency, but this is also the theta, which is the phase shift. So this is Ohm's law. We need the impedance, Zn is shown here. In this case we see the resistor again, and now here the total quantity of the reactances of the L and the C quantity squared. And the phase here will be then determined by this expression, which is the arctangent of the imaginary divided by the real part of this impedance. Now, if we now substitute the values given here in this example, we can calculate what the Zn is as a function of n, and that is shown here. So we can now substitute here 1, 3, 5, 7, 11, etc. And we can then calculate the corresponding impedance. In a similar form, we can calculate now the theta n. That's actually shown here. So every value for the omega 0, the inductor, and also the capacitor, everything is now substituted, and this is now simplified to this one. Again, you can substitute the value for the n here, and then you can calculate the corresponding phase in radians. Then the expressions are given for the load voltage and the load current as shown here. That's the first one. You see here the VDC, 4 times VDC n pi, so in a general form like so. And for the current is actually the same thing, just divide by the we have here, so divide by actually the formula, so the impedance, and also the phase shift we have seen here. So this is actually pretty similar, only changes the phase here and also the coefficient here in front. Everything of course with the odd indexes n1, 3, 5, 7, etc. Now we can generate a table. With this table we can calculate a lot of things. We see here the column where the indexes is 1, 3, 5, 7, 9, 11. This is the frequency, so 1 times the fundamental frequency, 3 times the fundamental frequency, etc. This is the VON, which are the amplitudes of the harmonics. We can see that for the 1, you can just calculate here by substituting here 1, so it will be then 400 over pi, and the next time will be then 400 over 3 pi, etc. So those are all here. The RMS value are calculated straightforward. Just take this column and then each of them divided by square root of 2, because every frequency component is pure sine wave. Impedance is also straightforward. You go actually to this this expression, this one Zn, and then you substitute there the n, or you can take of course this one directly and substitute there the n, and then you can calculate the required Zn for a specific n. The ION is calculated using Ohm's law. That is actually just the VO divided by the impedance. So then you get this one. That's just of course the amplitude of the load current components. And you get now these values if you go from 1 to 11. Of course you need to go up to infinity in theory, but this is good enough for most cases. And for the RMS values, you can also do the similar thing as we have done for the load voltage. You divide each component by square root of 2. Then you have this column. Here are the phases for each case, and you have also another column extra, which is then determining the how much power dissipated for each frequency component. So you see actually for the first harmonic, you see here 5.305 watts. The next one is then 25.45 watts. And the next one is then etc. So in similar form. And for that we can also determine later the required or absorbed load power. But how do we determine all these things? That is of course important. So let's go also to the RMS load voltage. Therefore that we need this column as said before, and then we use this formula, which is in general given by the average value of our load voltage. In this case 0, there is no average value, so this part, first part is 0. We have the first harmonic RMS value, third harmonic RMS value, fifth harmonic RMS value, and plus actually also 7th, 11th, 13th, 15th, etc. So you actually go up to the infinite index, and then you have in total 100 here. Okay, the RMS load current in similar form, we take this column, and that's shown here. Again, we have an RMS, the average load current, but in this case it's also 0. There is no average load current, so this part is 0. This is a general expression. This is, we have here 0.7284 to square this, third harmonic, square that one, fifth harmonic, square that one, also the other one, squared, 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 add them up, and then take the square root of the summation, you get now 1.9476 amps. So how do we calculate on this column? That's actually about the absorbed power. Now you can actually do that directly, you don't need this column. I will like to show you that in two ways. Directly is using just the RMS load current times R. That's just 10 times the RMS load current squared. You get now 37.93 watts. But if you want to also do the summation, you can also take now this column and do now the summation of all the power components, and then again the odd indexes only. So the load power component of the first harmonic, the third harmonic, the fifth harmonic, or add them all up, and you also get 37.93 watts. So that's of course also nice to see that these are exactly the same. Taking this all together, we continue with the next questions. The next one is the average source current. This is also straightforward using the power balance, because we know the power in must be equal to power out, because we have ideal switches, everything is ideal, all the components are ideal. We can say the VDC times the source current average must be the load voltage absorbed, and that can be also rewritten like so, and we have now 0.3793 amps. Okay. For the THD of the load voltage, and THD in general is given by this simple expression like so. So we have the RMS load voltage minus the RMS of the first harmonic of the load voltage, each squared, divided by the square root of the first harmonic of the RMS load voltage. Now actually we know these parameters. We only need the RMS load voltage and also the first harmonic of the RMS load voltage. And we know again, this is for repetition, that this was the expression for the components, the harmonics of our load voltage, and only add all the components. Now for the first one, we can calculate this one, but this one, 400 over pi is this 127.3, and if you divide by the square root of 2, you get actually this one, which is 90.03 volts. Now substitute this 100 here and this 90.03 here, then we get here 0.483%. This is the exact same as actually with the resistive load, and resistive inductive load doesn't matter because we only look at the nodes here. It doesn't matter what kind of components are here. So this is always the same for this type of circuit. But the load current will change drastically. We can now see how that works. Again, a similar expression for the THD, total harmonic distortion. Again, the RMS load current minus the first harmonic of the RMS load current, each squared, divided by the square of the RMS load current first harmonic. Again, taking the square root of this quantity. We also know this. We also know this actually because that's from a table. The first harmonic is actually here. And the total RMS load current is here. But in general, again, for the repetition, we know this is valid. Again, Ohm's law, and this was our impedance. And we know that this can be also written like so. And for NS1, we know from the table, which is 1.03 amps. Take this divided by the square root of 2, that you will get this one as we have here. Then we have substitute values. You get now 2.48. This is interesting. This is actually larger than 1. Normally we have smaller than 1 as a value here. So we have some percentage which is then lower than 100%. In this case it is 248%. So the distortion is quite high. And that is really because of this capacitor. And that is actually the effect on the load current harmonics. Okay, moving on to the simulation results, taking all the values we have determined here. This is the simulator circuit in Simulink using Simscape elements. You see here the VDC, 100 volts, the RLC in series, the switches here, the S1 and S1. These are the two switches which go on and off at the same time, and these are the switches which go on and off at the same time. So this was for the first half of the period switching frequency, and this was for the second half of the period of the switching frequency. And this is commanded or operated from this PWM signal, which has a duty cycle of 50%. So this is then commanded by like so. We measure here using the current sensor, the load current here, also the voltage here, and we all set it to the scope. We will see that shortly in the next slide. And here we have some values like the RMS and the THD for our load current, and also the similar one for the load voltage. Also have here RMS source current. Let's go one by one. The first one is RMS load voltage, which was 100, so that's checked. Load current, RMS load current, which is 1.95, so close to what we have. The source current, our average source current is 0.38 approximately, which is close to what we have. Very close to what we have. And THD here is 0.4834, also very close to what we have. And THD for the current here is 2.48, also very close to what we have. So we can say this is all checked. Going to the graphs, for the red one is our source current, the green one is our load current, and the yellow one is our load voltage. What you see is actually that let's start with load voltage. Is indeed as expected. It's just a square wave signal, the output, so that doesn't change. But what does change drastically compared to the previous examples, that the load current here is drastically distorted. Okay, it looks like maybe a sine wave, but it is much worse compared to the RL load in this case, and that's why that's also the reason why this THD is quite high in this example. This is our example considering the square wave inverter having an RLC load. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation, and see you next time in another video.